Michał Wrochna, but I'm not sure I would say properly Sergi Paris Université. Is it correct?
Yeah, it's more or less correct. You know it changes
okay.
time.
So the last session, today's session talk is on spectral actions on asymptotically Minkowski spaces. So we come from the Euclidean to Lorentzian regime. Okay. Michał,
that's right.
Your screen is yours.
Thank you very much, and thank you very much for the invitation. It's a great pleasure, especially that I'm not coming directly, certainly from the non-commutative geometry community, although there are some very, very interesting links. So I should say that I have more perspective coming from QFT on curved spacetimes. And incidentally, well, we all the time have to deal with non-ellipticity of operators. So we have to use some PD point of view with the generic absence of symmetries. So we're interested in what happens if you take arbitrary perturbations of spacetimes. And also what's crucial in this are singularities of propagators in relation to renormalization. And that's why we needed to have methods that are kind of as close to local geometry as possible. So inspired, for instance, by zeta regularization, and that really work directly in Lorentzian signature. So that's kind of what brought me into this topic of developing spectral actions directly in Lorentzian signature. But let me first start with the well-known situation, which was very well summarized in the talks before. So if you think of the compact Riemannian settings, then you can define a spectral zeta function of your Laplace Beltrami operator, and then classical results state that the zeta function is really have a meromorphic extension if you start with the real part of alpha sufficiently large, and it has poles, and you can compute the residue. And before going to the discussion of residue, so let me point out that there is also a local version of this, and instead of using multiplication operators, I will simply refer to Schwartz kernels and to their on-diagonal value, and then the meromorphic statement, it also works for those trace densities, if you like to call them. So the theorem that was advertised in the 90s follows, of course, from what was already well known at the time from elliptic theory, from what was known, in fact, on the level of heat kernels. It states that a very particular pole gives you the scalar curvature, and you can interpret this as a spectral action for a Euclidean gravity, because the variation of this, if you equate it to 0, and it's equivalent to Einstein equations. This has motivated definitions of scalar curvature in non-commutative geometry, and also actually plays an important role in quantum field theory. So later on, this was rephrased by Chamseddine in a form which we have also already seen yesterday, and extended in various settings as to yield, in particular, the standard model Lagrangian. So it's actually another angle that relates very, very well with what we're interested in quantum field theory. But the natural objection that you can have to all this is that unless proven otherwise, it doesn't have direct physical meanings, even if it produces you the right numbers, unless the underlying manifold is like in general relativity, unless it is really of Lorentzian signature. But things don't look very well if you treat this seriously. because the Lorentzian analog of the Laplace-Beltrami operator, well, it's not elliptic. You lose everything in the form of elliptic theory. It's not bounded from below, and so you don't expect really to have anything like the Lorentzian heat kernel. So all that means that you're in really great trouble. Though, nevertheless, there have been much progress in understanding the structures of Lorentzian non-commutative geometry. So I do not mean at all to be exhaustive about all those very different developments. I should perhaps just underline that there have been many attempts to use a transition from Euclidean to Lorentzian signature. So you formulate first a spectral action in Euclidean signature, and then you try to use the result of this to predict things in Lorentzian signature. So what I'm interested here is something different. I really want to have everything right from the start in Lorentzian signature.
And could you translate this quote of Kohn?
Oh, well, of course.
I don't speak French. So.
Of course, it's just about, the standard ending of a talk when you do many things in your Euclidean signature. And at the end, you say that, well, finally, let us state that we have not considered the important difference between Riemannian and Lorentzian signatures, right? So
okay, thank you.
That's the aspect I am interested in here. But in fact, there are several important clues about what it can actually do. Well, first of all, if you look at the local geometric quantities, such as the scalar curvature, it makes perfect sense in Lorentzian signature. And in fact, you can also define some formal heat kernel coefficients just by saying that okay, you change the signature in the transport equations, you solve them, and well, you have to switch signature. Everything is fine. So this is the reason why there is strong belief that there should be a Lorentzian theory indeed, and you can produce Lorentzian numbers from Euclidean computations. Even better, there's a thing called the Hadamard parametrics, which I will very much rely on in this talk. That is actually a parametrics for wave equations, so for really the Lorentzian thing. And if you look closely at it, it is well known that it actually will reproduce coefficients which are kind of equivalent to the heat kernel coefficients. So there is a local theory which is actually quite well understood and developed. On the other hand, much more surprisingly, it turns out that if you put good conditions at infinity of your space-time, then it is possible to show really that with respect to the canonical L2 scalar product that you have associated to the volume form, the Lorentzian metric, the Laplace-Beltrami operator, oh, what did I do? I don't know. It's actually essentially self-adjoint if you put the right kind of assumptions, and it's relatively easy to prove it on static spacetimes. If the coefficients do not depend on time, well, then essentially you can reduce yourself to the spectral theory of the spatial slices. But more surprisingly, it can be done so for perturbations of Minkowski space and more general spaces that have a similar structure at infinity. So, well, you have a global realization, an essential self-adjoint operator. So you take its closure, of course, you can define functions of it by functional calculus. Well, this is great, But is there anything like in the elliptic case that relates this local theory with this more exotic, perhaps more surprising global theory? So that's the question I'm mostly interested about here. And if you prove this, then you should be able to have a.
May I say something? What means exactly asymptotically static spacetimes? What does it mean exactly?
Oh well, it's a conjecture in terms which is not really written down and specified very explicitly. But what it means is that the coefficients of your metric are allowed to be time dependent, but that time dependence is smaller and smaller as you tend to with t to infinity. So there is
a control on this dependence of t. So,
yes, yeah. exactly.
Okay, good.
So what I want to show you is based on a joint work with my collaborator Viet Dang, who is right now in Lyon, and he's moving soon to Paris. Okay, so the main theorem is the following. We make indeed the same kind of assumptions that you need to have this essential self-adjointness, right? So we have to impose that it's globally hyperbolic. This is a very general class of space-times, just because we need to think of it as an evolution problem. And we assume that we have a perturbation of Minkowski space or a more general space-time. I will discuss the precise assumption later on. And for technical reasons, so far, we've done the work in even dimension. And then the tape theorem says that for each epsilon larger than 0, which you use to separate yourself from the spectrum, which can be the whole real line, well, you can define complex powers of your self-adjoint operator just by functional calculus, because you avoid the spectrum, right? And it turns out that, first of all, it has a Schwartz kernel indeed, and as in the Euclidean setting, if you take alpha sufficiently large, it has a well-defined on-diagonal restrictions. And this object, it extends as a meromorphic function with poles located exactly in the same place that you expect from the Riemannian signature. And up to a factor of I, you find as epsilon tends to 0, the same formula that you have in the Euclidean case. So it's really indeed the Lorentzian scalar curvature. The proof works directly in Lorentzian signature without assumptions, particular assumptions on some symmetries. And the very funny thing about it is that beside avoiding some low frequency problems in a way, this epsilon regularization is also responsible for the relationship with the Feynman propagator on curved spacetimes.
Sorry, I have a question, if you don't mind.
Go ahead.
I mean, is box self-adjoint, or formally self-adjoint at least somehow? Is it?
We are working here in the scalar case. So on any Lorentzian spacetime, it's going to be symmetric with respect to the canonical L2 inner product, which is a really honest, positive, definite inner product, right?
So this is the product you would use also for the Laplacian in the, correct?
Yeah.
Yeah.
However, with special assumptions, you know, for instance, if you're saying perturbations of Minkowski space, it's okay. Then it is actually essentially self-adjoint. And when I write things like this, I mean its closure. So there's really a self-adjoint operator here.
Yeah, I'm
non-Hilbert space setting.
Yeah, I'm missing something because you have just this Lorentzian metric, right? But then now all of a sudden you want a Euclidean, positive definite metric. How do you turn that into positive definite metric?
There is no positive definite metric. It's just that when you define the L2 space, you take the volume form. The volume form, it means that you integrate over something positive. So,
okay, right. Okay, yeah. These are the scalars. Okay, yeah, very good. Okay.
But you're right that beyond scalars, things get more tricky. That's one of the open questions here.
Okay, very good. Thank you. Yeah.
So perhaps I'll tell you more about the bibliography once more detail will be shown. But let me first focus indeed on this question of self-adjointness, and let me try to explain where do the assumptions come from, at least, right? So, the situation is as follows. So consider just the situation on Minkowski space. There is no t dependence or else of the coefficient, constant coefficient case, okay? And we'd like to make sense of the resultant of this operator. And the first intuition that, well, at least people from PD would have is, okay, I know how to write an inverse of P minus Z because I know how to solve Cauchy problems. And the inverse, which is associated usually to solving a Cauchy problem, is what we call the retarded propagator. So the formula is something like this if you write it as a Schwartz kernel in only the time variables. But you can see that this looks hopeless because if, say, the imaginary part of Z is larger than 0, then one of the two half groups behaves well. It has the correct decay, but the other one is just exponentially growing in Z. So that inverse is certainly not going to correspond to resolving. In fact, anything that is related, at least, to a Cauchy problem will behave very, very badly in Z and is of no use to this problem. But the solution comes naturally from physics and.
So what's the function theta t minus s in the?
Oh, it's heaviside theta. So. Characteristic function of the half line. So this is what you need
on the right, 0 on the left.
Yeah. So that's what you need to put to have to have an honest fundamental solution, right? But anyway, this is not the good one, and the good one is well known by physicists from a very, very long time. The idea is, okay, so you should reverse the direction of propagation for either the positive or the negative modes, and it gives you a neat formula like this, where at least you can expect to have some decays. And indeed, it is the case. It is really the resultant of self-adjoint operator. And when you make Z tend to the real axis from the correct direction, then this is indeed the Feynman propagator. But now, if you're on a general curve spacetime, so there's some non-trivial dependence on of the coefficients, then you can employ everything you know from partial differential equations. You can try to construct, say, as Fourier integral operators, or using tools of evolution equations, something that really resembles this formula. But there is a very serious problem. Those techniques, they allow you to write some formulas which are good modulo some smoothing terms. And the smoothing terms, they are usually completely irrelevant. You can solve them away with a Cauchy problem and so on. but they actually behave, they are actually Z-dependent, and you don't know how to solve them away, right? And you cannot solve them away using a Cauchy problem, because the Cauchy problem is really ill-behaved in Z. So actually, it turns out that it's difficult just to guess a formula for the resolvent and do it like that. You need to have some powerful estimates to do it. And the idea is that you should not expect to have this on a very, very general space-time. However, if at infinity, so say for large times, it behaves like the Minkowski metric, then you should be able to start there at infinity and use some estimates that will propagate the knowledge that everything is good from infinity to finite times. So this corresponds to propagation of singularities estimates kind of from infinity. And this is a subject which has had really, really exciting progress in the last few years. So there have been many new extensions of classical theorems of Remainder and Melrose, especially in the context of general relativity, of linearized Einstein equations and nonlinear Einstein equations, and it has been used in the proof of the black hole stability conjecture by Siemssen and Vasy in particular. But
may I ask a question?
Yes, go ahead.
Yeah, I mean, but at that point, you need some finite propagation property or something if you want to get a result. I mean, no? I mean, you are referring to all these works by your propagation estimates, but how do you do this? I mean, maybe it's too long to explain, but okay.
Yes, I mean, it is definitely too long to explain, but there is at least an intuition to gain. And the intuition, which I like to sell you, is that those estimates are based on what we call positive commutator estimates. We get an estimate from the fact that we have constructed a commutator that is positive. And commutator of operators at the leading order term, this corresponds to Poisson bracket of symbols. Mm-hmm. And then this becomes a problem from classical mechanics, and controlling those Poisson brackets is actually corresponds to having some positive quantities or some growing quantities along the null geodesic flow. So that's the reason why you can expect to have good estimates if you know something about the large time structure of the null geodesic flow. So this is precisely what is underneath the general assumptions I will state. Let me try to explain this. So the problem is that we will need to impose some conditions at infinity, and we are not always used to working at infinity. It's better to compact everything to have a more familiar language. So let's start with Minkowski space with its usual coordinates. And if you think only of the analysis part of the problem, then what you can do is that you can readily compactify it into a ball. Okay, so infinity in both spatial and time direction, it corresponds to the boundary of this ball. It's a sphere. But if you want to do serious analysis down to that boundary, you have to realize that the fact that the coefficients of your metric are translation invariant at the boundary, this translates to a different kind of regularity than just, taking derivatives and controlling this. It's because the boundary defining function, it's an inverse of the distance to the origin. And if you change your coordinates accordingly, you will get, it will become a kind of degenerate vector field where there is a rho square in front of it. So the idea of Melrose is that, okay, if these are the natural vector fields for doing analysis, then the natural bundle on which you will do the analysis is not the cotangent bundle, but it's rather the scattering bundle, which is C infinity generated by those were scaled one forms. And it is a kind of a long story of how precisely do you lift null geodesics to the level of that bundle. So that's what we call null by characteristics. But the important thing to get out of this is that we have good estimates if we make a non-trapping assumption. That means that there are some special sets inside of this scattering bundle at infinity, which are simply the endpoints of null by characteristics. So you should think of the null geodesic flow as going from minus infinity to plus infinity, but it's important that it's non-trapping in the sense that if you are a null geodesic, you are not allowed to go like that, of course, but you are also not allowed to stay in a finite region of space-time. You need to go away really also to spatial infinity. That's it in a nutshell. So it turns out that this kind of assumption, it includes small perturbations of Minkowski space, well, in particular, compactly supported ones. This is the simplest setting that you can imagine. And asymptotically Minkowski spacetimes in a very specific sense, where you say exactly how the coefficients behave at infinity. So this is what's underneath the proof of essential self-adjointness due recently by Vasy and generalized by Nakamura and Taira. So this corresponds really to inverting, P minus I0. So this is where this idea of Feynman inverses and of having true inverses by propagation estimates kicks in. Okay, but I should get back to the main point. The only thing I wanted to add is that, well, we assume indeed that we have non-trapping Lorentzian scattering spaces, so that's potentially more general than just perturbations of Minkowski space. And we also have spectral action in the form that's analog to Chamseddine cone action, with perhaps slight differences. Of course, you have to work a little bit more because there is this epsilon, but we control this. And thing which will become clear perhaps in a moment is that in a theorem you are not allowed to have arbitrarily, say, compactly supported test functions, but we need f to have a Fourier transform which is supported on a half line. And the coefficients that will appear here, they are better formulated in terms of the Fourier transform of it. So this is the Mellon transform of the Fourier transform. And the reason for this is that we need to be really careful about the whole spectrum. We can choose positivity of f, and if you want a function which will behave when you put this plus I epsilon, well, it needs to have good holomorphicity property in a half plane, right? So by Palivini Schwartz, this corresponds to this kind of assumption.
Excuse me. At that point, do you expect that you could generalize this class of function? You work with the Schwartz function. Could you expect a larger set of functions just to get the same result?
It's okay. I haven't checked this, but I think it's very, very likely that you will be able to extend it to more general functions or distributions as long as you have good holomorphicity properties above the real axis. So I would guess that you could do something if you have a distribution with whose Fourier transform is still supported in a half line. That will be my first guess. But I'll show you the formula, so this will look very natural to you, I think. All right. So how does this work? What's the idea? So we start with a relatively okay knowledge, at least of the resultant. That's our starting point. That's where the essential self-adjoint comes from. So if we start from the resultant and we cannot do the heat kernel, okay, so let's try to do complex powers, and we can define those complex powers, of course, by abstract functional calculus, but it's more convenient to have slightly more explicit representation in terms of contour integrals. And a good contour, so you think of having the spectrum of the real axis, well, it's the contour which I have drawn right here. And if you are used to positive operators, of course, this might look very weird because you are used to going around of the spectrum. But if you think you can, of course, also deform this contour a little bit, and here it's the good choice because you will not hit the spectrum in this way. Or alternatively, you can think of not P but IP and use simply the functional calculus for sectorial operators. So either way, you will be able to show this formula if alpha is equal to n plus some small mu, say between 0 and 1. Okay, so how do you hope to extract any kind of local geometric information? So the idea, well, which is present in the physics literature about QFT on curved spacetime, is that, well, what you can hope to have is a kind of geometric parametrics, which is the Hadamard parametrics. So I will be more precise about it in the next few slides. But the whole problem at the very heart of it is that this relatively well-studied Hadamard parametrics, you have to show that it's really an approximation of the resultant, and uniformly in Z, because afterwards you need to integrate in Z to obtain the complex powers. So this is the part in red, which I will stress many times, because this is the part that requires assumptions. This is the part where there is some difficult analysis. But then once this is done, you are again on familiar ground. You can just forget about the true resultant, and you can work with the Hadamard parametrics, and it has many features in common in terms of how you do it with the heat kernel, indeed. So it works really like a replacement of the heat kernel in this situation. So what is the Hadamard parametrics in this context? So the idea is that first you look at what's going on in the massless case for Minkowski space, and you'll realize that, well, the Feynman inverse is simply given by a special case of this Fourier transformed formula, where there is actually this I0 regularization that's present, and it will have nice properties if you put here this this gamma factor, and then you work close to the diagonal. We are trying to approximate Schwartz kernels, remember. And there you can use normal coordinates. Of course, you would work in normal coordinates, and you simply state that in those local coordinates close to the diagonal, you are going to extend this formula to the curved case. I think it's well known that if you define distributions of this kind, well, here with this added subtlety, then they will satisfy some very nice relations. And if you look at those relations, it becomes obvious that if you postulate an ansatz, which is locally defined at least, formal ansatz of this kind, well, it's possible to arrange the coefficients in here, which are some unknown smooth functions, to satisfy transport equations, and then you solve those transport equations. So this formal Hadamard parametrics, you can manipulate with it in the same way that you would construct the formal heat kernel, and the tricks used to do it are actually very, very similar. Well, here, of course, you need to do some estimates in terms of the dependence of Z, just quite complicated because of the light cone singularities. But we do it in a way that's that kind of generalize what in the Riemannian case is what you can find in Hermander's book or in the lecture note by Starge. Okay, so that's the definition of the formal Hadamard parametrics. But to really use it in your problem, well, you have to define a Vieta distribution, which is defined everywhere. So what you would do is that you will localize it with some, smooth function supported near the diagonal, and then you check, okay, what happens if I act with my operator on it, and you will get the determinant of G minus 1/2 times the identity. You will have some terms which behave so rather nicely as you increase the accuracy, as you increase the n. However, there is a huge problem with the term that remains when you hit with derivatives on this chi function. You have actually the same problem when you work in the Euclidean case, but then what you do is that you solve away this term using the inverse of p minus z. So by ellipticity, there is no big problem, and the fact that this term is 0 near the diagonal, it saves the day, because the term with which you have solved away, it will re-enter into something that does not play a role when you take coinciding limit points, and when you consider the meromorphic extension, in particular, it doesn't enter the pole. So once you know those things, you immediately discard this term in your head. You just totally forget about it. Right? But here it turns out that this is really the core of the problem. It's a singular distribution. To solve it away, you need to have the refined information about singularities of the Schwartz kernel of your resolvent. And beside that, you need to have this information in a way that's uniform in Z, so that when you integrate those things afterwards, they don't become a problem. So just perhaps to indicate you what this is relate to, the game is to prove microlocal estimates, in the sense that you cannot hope to show that P minus Z minus 1, that the resolvent is regularizing, right? So it's impossible even in the elliptic case, but at least there are some directions in the phase space, namely, you can hope that after composition with some pseudodimensional operators that are elliptic at some particular points, things are going to be well. So in the elliptic case, you have it's enough that you avoid the diagonal in this way, and here you have all the singularities that you would have in a hyperbolic problem, and you have to show that you don't have more of those singularities. So this is what I could call having Feynman wavefront set. Okay, so let me leave.
So sorry, you mean all singularities are on the wavefronts? Yeah.
So this is actually an operatorial version of the wavefront set, which is uniform in Z. But the first intuition is correct. It's an estimate about the wavefront set. You want to have a good estimate on the wavefront set so that you can compose the distributions, right? Exactly. Compose the Schwartz kernels and estimate
and this Rn, where are singularities of Rn? You say it's singular, but zero near diagonal. Where are they? I mean, are they?
Well, they are way off the diagonal.
Oh, okay, but on the diagonal is zero, you're saying?
Yes. But the thing is, when you solve it away with the resolvent, you act with a global operator that spreads it everywhere. And what you need to prove, it's okay, it had spread support everywhere, but there are no on-diagonal singularities that it generates.
So that's the exact opposite of, exact opposite of, I mean, for positive definite case or something like that. Yeah. Well, I mean, if you look at resolvents, I mean, usually they have singularities on the diagonal, but away from diagonal, they are nice. Yeah.
Yes, that's correct. That's the difference here. It's no longer a pseudodimensional operator, so it has nastier singularities that you need to control. And in general, things are very bad, but the Feynman wavefront set, if you have the same wavefront set that you would have for the Feynman propagator on Minkowski space, things are good because it has a kind of involutive form, and you can do compositions and other stuff. Let me leave this for a moment, because this that's the kind of heavy technical part, but let me at least outline the things that should look more familiar, which is once you have done this, how do you extract the curvature? And you will see that there are many analogous things that you know very well in the Euclidean case. So now that we know that we can replace a resolvent by this Hadamard parametrics, so as far as complex powers, if you're interested in complex powers, then simply you should take contour integrals that involves those families of elementary distributions. They have a very, very nice property. If you take the integral of one of those, you will get another one with a huge lot of gamma factors, and you will recover the meromorphic structure in the same way that you would do in the Riemannian case. So to compute the pulse, actually, it's we find that it's useful to do a Vic rotation once you work at the local level, really with quadratic forms, and you have some, Gaussian integrals with some quadratic forms, and you change the signature in your quadratic form, and you get the correct results. But this works only at the local level, of course. And then once you have meromorphic structure, so once you have your local zeta function, all you can try to deduce how things look like for a function of it by a Millen transform argument. And it's a kind of miracle that it works because of this problem with the spectral, which is bounded of below. So the trick that saves the day is that you can actually write rather a formula for the Millen transform of the Fourier transform, and then by Fourier inversion formula and Mellin inversion formula, you will get a formula that says you that f of t plus I epsilon, remember this is what we want to apply the functional calculus to, it's given in a nice way in terms of this Mellin transform of the Fourier transform. So then there is no kind of contradiction. You can take the Mellin transform of this if you have assumed those support properties, and you have an inversion formula for functions which have good analytical properties, at least from one of the two half planes. And then the scalar curvature, well, it's obtained exactly as expected. So there is not much new in it, and you will see that this is the same trick that appeared in a talk yesterday, in which you represent p using this logarithm of the determinant power 1/2, and you also extract the relevant terms by looking exactly in this way at the transport equations and interpreting the scalar curvature in terms, of an expansion of the matrix, if you want, in normal coordinates. So you always work in normal coordinates in a very small neighborhood close to a point. So I don't have much time to explain to you the proof of this remaining crucial part. So I will just very, very briefly say that there is one regularity properties that guarantee you at least that you have a well-defined trace densities for large ends. It essentially follows from the same radial estimates or propagation estimates that are used in the proof of the essential self-adjointness by Vasy. And we need to construct another parametrics in terms of evolution problems for PDEs that resembles the formulas for the Feynman propagators I showed you this on the slide with the photo of Feynman, just for the sake of having this estimate on the wavefront set. So it's easier to do it on the level of that parametrics and then show that this parametrics is a good approximation using, again, a propagation estimate argument. Okay, so I will not talk about the details of that. So let me just point out perhaps a list of similarities and new features when you compare the two cases. So you've seen it clearly that this is the same structure of poles, same form of local geometrical terms, and those Hadamard coefficients, they are related in a well-known way to heat coefficients that are that you obtain by changing simply the signature in an obvious way. So in this way, you could justify many of the computations that are done in the Euclidean case. On the other hand, you see that there are some new features. So for instance, in the global analysis, there's a special role played by non-geodesic flow. So in fact, we don't understand very well what's the domain of the operator and so on, but it seems to be clear that this is an operator which knows a very great deal about the non-geodesic flow. Another crucial difference is that in elliptic problems, if you have an elliptic operator of order 2, then you gain 2 in regularity when you take an inverse. So when P it differentiate twice, you lose twice, but you can recover it back by taking an elliptic inverse, right? Here it's not the case, and it's not a kind of a side product of the proofs or anything like this. It's a very general phenomenon. If you have something that you could call an inverse for an elliptic operator in some sense, you always expect to have this one loss of regularity, and it does happen, for instance, here for the Riemannian, and it's actually very annoying because it means that there are many commutator arguments that you would like to run, but that simply won't work. So this is clearly different from the elliptic settings. A point which is related to one of those with one of your questions, it's the fact that the resultant complex powers are not differential operators. In a sense, they have 2 singular symbols for this, but if you want, you could describe it in terms of Fourier integral operators, or more precisely what's called paired Lagrangian distributions. But perhaps you also don't need to know the details of this, because anyway you have a very explicit parametrics for that. Okay, and I've pointed out already the relationship with Feynman inverses and the fact that the unbounded from below spectrum, it makes conditions on this function f necessary. So to sum up, we have shown that the self-adjoint realization of box is related to spacetime geometries in a way that parallels elliptic case as much as possible, at least under the good assumptions at spacetime infinity. And to me, it really means that you can say, without saying that you need to restrict to the elliptic case or something like that, you can really say that gravity can be derived from a spectral action. And perhaps a small remark that while we get various extensions, so perhaps the one to emphasize that is that in that setting you can also have a good notion of Wojcicki residue using a kind of scaling procedure which is really reminiscent of the works by Kohn and Moscovici. All right, so that's pretty much it, and I thank you very warmly for your attention.
Interesting, very interesting talk. There were some questions.